All right, so what we're going to do is we're going to find the odd valent vertices. So I've got odd valent vertices here and here. And if there's an edge connecting them, I'm going to duplicate that edge. Okay, and so here I have a duplicated edge. Now all the valences are even. And so if I choose a starting point, let's choose A, I can go through and find an Euler circuit. And I just numbered the order in which I went, and so now I have an Euler circuit. So that is step 2. Step 3 is squeezing that Euler circuit onto the original graph. So it's just a matter of copying down the same circuit. And instead of duplicating the edge this time, I just write 2 numbers on that edge. So this one is the Eulerize graph, and this is the squeezed graph. What I did yesterday. All right, so I've got 2 odd valent vertices. Now it would be nice if we could just do this. But what would that mean? Creating a new road. And so we don't want to do that. We want to use existing edges or existing roads. So I'm going to follow this. Now this was at 4. This vertice was at 4. I added 2 edges to it, and so it's still even. It's now at 6. This is going to be the shortest path to the other odd valent from X to Y. I could also go down this way, but that way is longer. All right, so I want to make sure I use the shortest path. All right. All right, when I have a rectangular network, I have a number of odd valent vertices, and so my odd valent vertices happen on these highlighted vertices. Now, the most common error on this is just to connect all the odd valent vertices like this. What happens with this vertice? What is the new valence? It's 5, and so by connecting this initially, I went from 3 to 4, 3 to 4, but by adding an extra edge, I went from 3 to 4, then back to 5, and so now this one is still odd. So I want to get rid of that second one, and I'm going to continue with this one, this highlighted vertice, and I'm just going to walk the edges. So now this one's at 4, this one went from 2 to 4, B did, and then I continued on. And so this is the technique called an edge walker. And so I'm just going to walk the edges and making sure that once I'm even, I don't repeat another edge to make it odd. So here, when I get to this vertice, I have to go along the edge to get to the next one, and along the edge to get to the next one. Now all of my valences are even, and I could find an Euler circuit. There's too many edges here. We're not going to go through the Euler circuit from there. So on this graph, we have 4 edges that we need to repeat. Now, if I looked at this, I have 8 total odd valent vertices. 8 divided by 2 is 4. And so an abstract question where I said there is a total of 18 odd valent vertices, how many edges would you need to repeat without giving you a graph? What would you say? 9. We would just divide that by 2. So that is kind of an abstract question without a graph. So on this next one, we have these as odd valent vertices. I have a total of 10. So if that were an abstract question, what would the total number of vertices be, or repeated edges? 5. Okay, for this one, I'd like you to go through and walk the edge and tell me how many repeated edges. 5 is the minimum. You might not get it done in 5, so go ahead and do that. If you got 6, this is my guess on what you did. You most likely went like this, correct? Now what's wrong with this? This vertice and this vertice are still odd. When I added this edge, it became even, and when I added another edge out of it, it became odd. So that doesn't work. If I started here with the edge walker, I'm now even. These are even. Now I have to repeat down this way. Repeat the edges until I get all of the valences that are even. And now this is an Eulerized graph.